I am Candace Shively with Utah State University Extension, and these monthly webinars are supported by USU's Center for Water Efficient Landscaping. Today, we have Shane Evans with us. Shane's a grad student with USU who was recently hired as the lawn and water conservation educator with the University of Minnesota. So he is doing this webinar today, and he's defending his thesis on Friday, and then he's heading to Minnesota on Saturday. So he's got a busy week, exciting week ahead of him. His topic today, he's going to talk about smart irrigation controllers, and they are a hot topic right now. Many homeowners are installing them. Many water districts are offering rebates to encourage their installation. So it's appropriate that the focus of his thesis was to determine how these controllers affect water conservation in the urban landscape. So with that, I will turn it over to Shane.
And I think we're ready to go. Thank you for that introduction. As she mentioned, I'm Shane Evans, almost graduated student, still a graduate student here at Utah State University. And today I want to talk a little bit, as you can see there, about smart and manually programmed irrigation controllers. So to dive in just straight away, I want to give you a quick overview of what I'm going to be talking about. I want to give you a little bit of history behind irrigation, kind of where we started and where we are now with smart irrigation controllers, and ultimately talking a little bit about how they work. But the majority of the time I want to spend talking about my research project and some of the results and conclusions that we found. But the picture you see here on the right is actually the research site there in Logan, Utah at the Greenville Research Station, or research farm, I should say. So to start, we go all the way back to 2000 BC. This is kind of the first time that they saw concrete tubes being used to move water. The Roman Empire was growing, didn't have enough water, and so they kind of, were the first people to actually move water from one place to another so they could have enough irrigation water for their bathhouses, for drinking water, things like that. And an interesting book that I've read, Water 4.0 there, it talks about the evolutions of water, and it starts with Water 1.0 and the Romans. So it goes into a lot more detail than I just did there. But kind of getting into, I guess, modern day irrigation, around the turn of the century in 1900, we started to see our first little sprinkler heads pop up with the advent of rubber hoses, things like that. So on the picture there, you see, on the left, a one-hole sprinkler, and on the right, a couple decades later, you can see the advances that they've made. But with World War I happening and then World War II happening, there's a lot more industrial cities, a lot of people moving into neighborhoods, and they started to see a need for irrigation controllers rather than just, a sprinkler that you move around your lawn, which is actually still even used today. But those first irrigation controllers, you can see here there's a picture of a Moody Rainmaster from 1950. And it's kind of cool to see that technology has advanced, but the principles are still the same. So this clock you see here, this tells you the time of day that you want to start the irrigation. This little thing here, the little cog there, is the days that you want to water. And then these down here are actually your irrigation zones. As each of these little bars touches the metal there, it signals, okay, this irrigation zone needs to turn on. But it wasn't quite fully automated. But 10 years later, after some advances, they were able to create a fully automated irrigation system. And you can see similarly, there's the clock of when to start the irrigation, the days to water, and then your 6 zones in this case that you could program. That kind of moves us up to today, where most people who have any experience with irrigation controllers have seen something like this. We have a Hunter controller on the left and a Rainbird on the right. But the principles are still the same, where you choose the days you want to water, you choose how long you want to water, when you want it to start. And, it's kind of cool to see the principles are still the same even today. But moving into smart irrigation controllers in the last 20 years, we've had the creation of some soil moisture sensor-based irrigation controllers, and also some weather station-based irrigation controllers that I'll talk a little bit more in the next couple of slides. But my research has been focused on these Wi-Fi enabled irrigation controllers. They all require a smartphone. You know, there's an application associated with the controller that you can do a lot of things with it. You can receive notifications on when your irrigation system is watering, when it stops. And I have the ones bolded that I've been working with, which are the Rachio, the Beehive, and the Skydrop controllers. Something of note though, bigger companies such as Scott, Rainbird, and Hunter, they also have excuse me, these Wi-Fi enabled irrigation controllers. But going back to the more soil moisture sensor based controllers, there's essentially two types. You have the suspended cycle irrigation controller, and it's very similar to a manually programmed controller. You have a schedule, you have the times you want it to start, how long you want it to water for. But the difference is if the soil moisture sensor says, no, there's enough water in the soil, it'll kind of skip and cancel the next irrigation event. The second type there you can read is the water on demand irrigation controllers. They don't really require any programming. Basically, it has the user set a low and an upper threshold for your soil moisture content. So if your soil reaches permanent wilting point at say 15% volumetric water content, you might set the threshold to be 20% so that when the when the soil gets below that 20% threshold, the irrigation system will kick on at the start time that you set it to start on. Moving on to weather-based irrigation controllers. They use an on-site weather station, as you see there, to collect continuous ET measurements. And if you're not familiar with the term ET, it stands for evapotranspiration. And so it breaks up the word evaporation and transpiration and combines them. So evaporation is the water that's lost from wind going across the landscape or the sun, beating down, and transpiration is the water lost by the plant as it, I guess you could say, breathes. But that information is sent to the controller, and decisions are made by the irrigation controller if it should irrigate based on what the weather station is telling it to do. Then there's also historic ET-based controllers. These are a little more simple. They're pre-programmed and they're based on historic ET values depending on, and you can choose that based on the region that you live in. Again, focusing on Wi-Fi enabled irrigation controllers, what I've been working with. They sometimes call them signal-based controllers. And so they use that same data from a publicly available weather station that calculates that ET value. And then that ET data is sent to the controller, within the case of the controllers I was using, through a home Wi-Fi network. And that's kind of what we tried to simulate with our research. So getting right into my research, you can read there, the title of my thesis is The Effects of Wi-Fi Enabled Smart Irrigation Controllers on Water Use and Plant Health in Residential Landscapes in the Intermountain West. And one reason we put plant health in there is, if a smart controller saves you a whole lot of water, but you have a yellow, crispy landscape, people aren't going to want that. So we also wanted to take a look at plant health and see how that was affected. But one reason for this research, especially here in the Intermountain West, is I want to focus your attention to this purple circle in the bottom right-hand corner. On this graph, you'll notice on the x-axis we have projected change in population, and on the y-axis, average annual precipitation. So the states here that are projected to have the highest increase in population are also the states that have the lowest average annual precipitation. So if a state's going to keep growing, included in this little circle, we have Utah, Arizona, Idaho, Nevada, Montana, Wyoming, a lot of states here in the Intermountain West. And if the population is going to grow, we need to figure out how we can conserve water, since we don't actually receive a whole lot of annual precipitation when compared to other states. And an area that we thought this could be done in is in residential landscapes. Just about every home has some grass in it, and it needs to be irrigated, multiple times a week. And in fact, we learned that turf grass, or grass that's in your lawn, is the most irrigated crop in the country. There's around 12 million hectares of it in the United States, and about 60% of that is considered urban irrigated turf grass area. And to kind of put that in perspective, 7 million hectares is basically the state of South Carolina being covered completely in grass and having a giant irrigation system running through it. So there's a lot of grass out there that's being watered by irrigation systems. And then here at the bottom, you can see average American households, they use around 1,200 liters of water a day. And 30% of that is considered to be used in the outdoors. Now, not all of that goes to watering landscapes, but a big percentage of it does. And here in the state of Utah, that number actually bumps up to 60-65% of water going toward outdoor use. So again, another reason why the research is important here, especially in the state of Utah. Speaking of Utah, it has the second highest water use per capita. So we use around 240 gallons of water per person per day. And kind of going back to that figure I showed earlier, we only receive around 13 inches of precipitation annually, but most of that occurs in the wintertime in the form of snow. So long, hot, dry summers and with periodic drought. And I have a picture here, of 2018, September 2018. These darker areas show more severe drought, whereas in 2019, we see some, the white means no drought, yellow and kind of the tan, some more intermediate drought type of type of years. And so this last year was, a pretty good year for us, but we do have periodic droughts. So some of the objectives of this study is to determine if those Wi-Fi irrigation controllers, do they conserve water compared to a typical Utah homeowner, and, to manually program controllers. So in order to do that, we wanted to quantify the amount of water applied by each of the controllers. Then we also wanted to evaluate plant health. I mentioned that earlier because you may save water, but if your landscape's dead, no one wants that. And then ultimately, we compared the measurements for each of the controllers or the treatments to determine if there was any significant differences among them. So it was a completely randomized block design. There was around 225 square feet of Kentucky bluegrass. The majority of the state of Utah has Kentucky bluegrass being grown in the lawns. And in each of these 15 by 15 foot plots here, there was a sprinkler head on each corner, and those are Hunter MP rotor sprinklers, and that's kind of their spray pattern you can see there. So kind of on a funny side note, before we even got started, we had a water line. Our main water line wasn't working, it was broke, so we had to dig it up. And once we finally got everything organized, we were able to start doing our own personal water audits. So we compared total water use from our controllers to the average Utah homeowner, and we used the same pattern here with the water audits. And that URL you see down there is a link to how you perform a water audit, and they have irrigation schedules for all 29 counties in the state of Utah. But in order to determine your distribution uniformity of your irrigation system, you put out these little catch cups, and then say after 20 minutes you go and collect water. You see how much water is in each of the cups, and typically there's going to be more water in the middle of the area than on the edges. And so using that distribution uniformity, it kind of gives you an idea of how much you need to water in order to make sure that the edges also get enough water. But as I mentioned, there's also an irrigation schedule recommended with these fact sheets that you see down there. And speaking of our Hunter controller, it was the experimental control for the experiment. And it was programmed according to those USU extension recommendations. And if I remember right, for Cache County, where we are located, we were supposed to, in the month of May, water every 4 days. In the months June and July, we watered every 3 days. In the month of August, every 4 days. And from September on, I believe it was every 6 days we were supposed to water. And so that's how the Hunter controller was programmed. And then the smart irrigation controllers, again, we chose the Beehive, the Skydrop, and the Ratio. They were programmed with an emergency-based schedule, which was in accordance with those extension recommendations. But then I guess you could say the smart part of the controller was able to take in the ET data from an on-site weather station and able to make decisions, how often they should irrigate and how much they should irrigate. And something of note with these three smart controllers, the Ratio is the only one that cannot be programmed at the controller. You must use the smartphone application to program the Ratio, whereas the Skydrop and Beehive controllers can also be programmed from the controller. And these were chosen because they are part of the rebate program offered, through Utah Water Savers. And there's a link to their website down there. And you have to make an account in order to get some accurate information as to which rebates are available to you depending on your area. But all of these controllers at the start of the study were labeled as EPA WaterSense approved. And in order to receive that rebate, you do need to have one of those WaterSense approved smart irrigation controllers installed in your home. And a list of those can be found at that Water Savers website if you do a few clicks, or you can do that second link at the EPA.gov, and that'll give you a direct list of all the controllers and other items such as washers and dryers that meet that EPA WaterSense standard too. But as you set up an irrigation zone, this is something that you might see when you open up the application on your smartphone. Now, there's a lot going on here, but essentially you're being asked simple questions such as, what are you growing? What's the soil type? And I decided to make a list here showing, the questions that you get asked by the smartphone applications. But something that they all have in common is they ask you your vegetation type, soil type, your number and type of sprinklers, sun exposure and slope. And then the Ratio and the Skydrop Beehive controllers ask you a few more questions regarding maybe, your plant factor, how efficient your irrigation system is. Whereas the Skydrop tries to keep it a little more simple and doesn't ask these questions, which, if there's a dash, that denotes I was not asked that question when setting up an irrigation zone. But another thing they all have in common is they ask you to choose a weather station. You don't have one that connects to the controller itself. You don't need a soil moisture sensor. So for consistency amongst the controllers for our project, we chose to use the Greenville Research Weather Station that you see there pictured on the right. And that is what the controllers used as their ET-based calculations. And based on the data they received, the controllers altered that schedule that I gave them as an emergency-based schedule. Now, we also wanted to know exactly what was happening with the plant. And since we're growing Kentucky bluegrass, we decided to make literal tubes of grass. So this tube that you see here on the left it's called a lysimeter. It's probably about 2 feet long, and it's full of soil with some grass on top. And this gives us a very accurate estimate of how much water the plant is actually using. And we figure that out by hanging it from a very precise scale. So it's being hung from a scale by these 4 chains here. And let's say, yesterday at 5 a.m., this tube weighed 100 grams. But at 5 a.m. today, when it was measured, it weighed 95 grams. That means 5 grams of water were lost through evapotranspiration. And that water is replaced by these 3 drip emitters. So they're going to put 5 grams of water into this so we can accurately see exactly how much water the plants are using. So to get into some of the results, here you'll see we have maximum air temperature are these black lines for 2018 and 2019. And you can kind of see as we get later into August, into September, the temperature starts to dip. But the other thing you can notice, as I mentioned, Utah is prone to hot, dry summers. In 2018, these bars denote precipitation events or rain events. and we only recorded around ½ an inch of water that actually rained on the plots from June 30th to September 30th. So very dry in 2018, which was reflected in that drought map I showed you. But in 2018, we saw similar trends up until September, where we had a much wetter September than Utah is used to seeing. And that'll kind of be reflected in the amount of water applied by the controllers that you'll see a little bit later here. Getting into 2018, first I want to point out we have this dotted line going through. That's the actual evapotranspiration that was lost, water that was lost by the plants from those weighing lysimeters I just showed you. And a couple of things to note here is the ratio, the blue here, and the beehive controllers, the yellow, tend to water more than that ETA value that's shown there. And then on the opposite side of the coin, the hunter controller, the green here, and the skydrop controller, they tended to water less than that ETA value that was calculated for each week. But what does this look like from a statistical standpoint? We ran some statistics, and to kind of give you just a quick overview, if we look at week 26 here, you'll notice that the letters are not different at all. And what that is basically meaning is there's no significant difference in the amount of water applied between the controllers. So even though you see the hunter controller waters less than the ratio did, there wasn't a significant difference. But if we go to week 27, we'll notice the skydrop here has an A, and all the other controllers have different letters. And that means the skydrop controller watered significantly less than all of the other controllers that we were looking at. And so that trend kind of continues throughout till we get to September, where again we start to see there isn't much of a significant difference in the amount of water applied. We also looked, at soil moisture. We wanted to look at some plant health measurements. And, if the ratio and the beehive controllers watered more, what does that look like from a plant health perspective, from a soil moisture perspective? So we use the Campbell Scientific instrument here, and soil moisture results kind of indicate, well, the ratio and the beehive controllers applied more water, and it shows here in the soil moisture. They typically have higher values of soil volumetric water content than that of the hunter and the skydrop controllers. And again, we ran the statistics on that, and we didn't start to see consistent, significant differences in the amount of soil moisture until about week 30 of the experiment, which would be roughly the middle of July. And then those changes kind of continue on throughout the rest of the season. We also looked at NDVI, percent green cover, and canopy temperature, but I'm just going to focus on NDVI here, which stands for the Normalized Differential Vegetation Index. And what this basically is NDVI readings are between 0 and 1. If you get a reading close to 0, you're going to have something that looks like just bare soil. And the closer you are to 1, that means you have, a very green landscape. And so as we took these measurements, again, we kind of saw the trend of the ratio and the beehive controllers showing higher amounts of NDVI, in this case, around 0.7, 0.72, consistently throughout 2018, whereas the hunter and the skydrop tend, you can kind of see the trend there. And again, that makes sense since the ratio and the beehive controllers tended to apply more water than the hunter and skydrop controllers. And again, looking at the significant differences there, we don't see significant differences until week 31 of the experiment. And to kind of give you an idea of what this looks like visually, you can see here's some pictures taken from a drone. Week 26, if you kind of notice here, they're pretty similar to each other. And you can see, they're pretty similar as far as looking at them. Week 31, when we started to see those significant differences, statistically, you can kind of see the ratio and the beehive are, fairly green, and you start to see maybe a couple little dry spots in the hunter and skydrop controllers. By week 38 of the experiment, again, the ratio and the beehive are fairly green, with the skydrop and hunter showing some yellow spots there. So I don't want to get into too many details of 2019. What I will say is the three smart irrigation controllers watered less. All three of them watered less in 2019 as compared to 2018. But the same general trend continues with the Ratio, the blue here, and the Beehive, the yellow, tending to water more than that ETA line that I was mentioning earlier, and the Hunter and the Skydrop typically watering less than that line. But in 2019, we had those big rain events. The Skydrop controller actually had a few rain skip events, whereas the other smart controllers did not, which is something we thought was interesting there. And again, there's just the, if there's significant differences amongst the means, you can see pretty consistently every week there's significant differences. Looking at soil moisture with the Ratio and Beehive specifically watering less than they did in 2018, you notice that the grouping of soil moisture, is pretty consistent throughout. But with that even being the case, we do still see some significant differences happening again up until, we get till the end of September. We start to see those significant differences aren't there as often. And a major reason for that is those rain events that we saw. And in DVI, we kind of see a similar trend besides the fact the Beehive controller, kind of has higher values. But when we look at our scale here again, our highest for the Beehive are around 0.68 with the lowest readings being around 0.61. But those differences, they are significant. There's several events where Beehive is significantly higher, has significantly higher readings of NDVI than the other three controllers. But again, what does that look like visually? Because that's what the homeowner cares about. If we look at these, again, we have our Hunter here, Ratio, Skydrop, and Beehive. At the beginning of 2019, again, we tried to have them all in similar states. Week 32 is where we started to see those significant differences. Beehive showing, still pretty green. And then week 38, after a few heavy rainstorms, you can see the Hunter and Skydrop controllers caught up, I guess you could say, to the Beehive and Ratio controllers. But that's, I guess, that's what rain can do. But getting into some of the conclusions, we did see significant differences in the amount of water applied by the controllers, soil moisture, and even the plant health measurements. When it comes to water application, some hard set numbers here is over the 2 years of the study, the Ratio controller applied 68 inches of water, the Orbit Beehive applied 67, the Hunter or the control for the experiment applied 44, and the Skydrop applying 43 inches of water. And what does that look like as compared to the average homeowner? Again, I can say all of these controllers, they did end up saving water when compared to the typical Utah homeowner. So the water check program, they've done hundreds of those water audits. And through those, they found out that, participants on average apply around 48 inches of water per year to their landscapes. And I like to imagine that as like a 4-foot swimming pool being, covering your whole yard. That's how much water is being applied throughout the growing season. So when you compare that to what the Orbit, Beehive, and Ratio controllers applied, they applied the most in our experiment, but when compared to those average homeowners, they do save you, over a foot of water per year. And when you're talking about hundreds, thousands of acres, a foot of water translates to a lot of gallons. And then looking at the Hunter and the Skydrop controllers, they used approximately 22 inches of water a year, or, basically half of what a typical homeowner uses. And that's where those USU extension recommendations came from. They did these water audits, found that participants are watering 48 inches a year, and found that that's, they're more than doubling what they needed to. And so I'll just kind of read this verbatim here, but when programmed according to USU extension recommendations, manually programmed controllers can be just as or more effective than Wi-Fi enabled smart irrigation controllers. We've learned a lot of people have the set it and forget it approach. And so if that's the case, these smart irrigation controllers can help conserve water. But if you're someone who likes to meticulously see how much water you're applying, things like that, a manually programmed controller can be just as effective as these smart irrigation controllers. Finally, one thing we learned is the ratio and the beehive have a lot more room for error when you're programming them. For example, they ask you, a lot of extra questions that a typical homeowner may not know the answer to. They may not know, what the permanent wilting point for their soil is. They may not know how deep the roots go. And so something we thought might be interesting to look at in further research is how is irrigation affected and how is water use affected by, making a mistake while programming these controllers. But that's about all I have for you today. And this wouldn't be possible without the members of my committee and the organizations that help fund this research. That includes the CWEL group here at USU, the Utah Division of Natural Resources, and the Weber Basin Water Conservancy District.
As always, this is being recorded. We'll get this edited and up on our website, hopefully within the next couple of weeks. Thanks everyone for coming, and Shane, again, thank you, and good luck with your career and your defense on Friday. This was probably
okay.
Really
thank you. These questions were good preparation, so thank you.
Good. I'm glad. All right. Well, everybody, enjoy the rest of your day, and we'll see you next month.